Okay, okay. So very good evening, all. So today, what I am gonna do, at first, from previous classes or the courses, people have posted some doubts. I'm going to ad- address those, and then I am going to solve some assignment problems. So let's start today's live session. So very good evening all, and welcome to the live session 2 for this course, a study guide in organic retrosynthesis. And I am Monosis Nandi, the TA for this course. So let's at first, as I told earlier, I am going to address some queries from the students. So people seems to have some problem regarding let me uh, regarding appendage disconnection and ring disconnection. So what is appendage disconnection? So appendage are some structural subunits consisting of one or more carbon atoms in their uh, more carbon atoms in and their substituents, which is bonded to a ring or functional group of origin. So let's take this as a target molecule. So this is TGT. This is TGT. Yeah. So there are various ways we can disconnect the molecule and make it small fragments. So one of the easiest way is to fragment or to flip this bond and this bond. So if we do that, we generate here this type of five member ring, which has which have an alpha beta unsaturated keto moiety, and this way it is protected with a protecting group or TPDMS, which is nothing but this group, tetrabutyl dimethyl silane. So the protecting group, termed as TPDMS, or you can say as TBS protection also. Yeah, so this is one of the appendage, and what are the other two? You can see, if we disconnect here, we can thought of connecting it an uh, by an thinking of an electrophilic attack here, as it is an Michael acceptor. When the nucleophile attack here carbanion type of thing will generate, and can attack an electrophilic or electrophilic group and do the substitution. So that's why they have incorporated the iodine. And here it is nothing but we have discussed in the previous class. It is nothing but an the Michael addition. So that's why this is an copper. So you know this is an soft nucleophile. So it would prefer the 1,4 addition over 1,2 addition. That's why this is chosen. So this kind of disconnections are known as appendage disconnection, as we are generating three moieties which have definitely more than one carbon atoms, and they are particularly well known or can easily be made. So in this way we can generate appendages. And this is another example. This is let's say this is our target molecule. So how can we synthesize that? At first we just thought of making it from the double bond. And how can we do this? By simple hydrogen palladium reduction we can do the same. And this is nothing but 4 plus 2 cycloaddition, uh, which is nothing but an Diels-Alder reaction. So for Diels-Alder reaction we generally disconnect these two bonds and generate one diene and dienophile. So you can see easily the diene and dienophiles are generated, and as this again this we have disconnected two bonds and make us two easily available molecules, and by simple Diels-Alder reaction we can make this. So this is also an example of appendage disconnection. So what is ring disconnection? So let's say we have not done that two bond disconnection. We have clipped just one. So if we clip this one, you can simply thought of this molecule. So from here to here, how we can do that? So with here they have H minus with nothing but sodium hydride, and let's say it happens in room temperature. So as we all know, in room temperature, uh, thermodynamic 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 stable products are formed, and for this case enolates are generating. So thermodynamically stable enolate should be formed. So that's why the TCP enolate would be here. As you can see, this is more stable enolate, and if the negative charge is here, it is less stable. So the negative charge would prefer, the enolate would prefer in this direction, and then simple and nucleophilic attack to the aldehyde group, which is nothing but aldol reaction. So this is general ring disconnection, example of a ring disconnection. So let's say if a single molecule, or if in a common molecule, how we can do the both things. So let's say this is the target product. So you can see both are the same. This is the target our target molecule. So TGT. So if we disconnect these two bonds and generate one diene molecule and dienophile molecule like this way. So this is nothing but 4 plus 2, and we are disconnecting two bonds and generating two simply available starting materials. So that's why these are two appendages. So this is an APD disconnection. And let's say we are not doing like this two bond disconnection, and we simply clip one bond here. So if we clip one bond here, so we can thought of the symptoms which let's say this can be negatively charged and this can be positively charged. As you can see, this is an symmetric molecule, so there are the other way around would be same, so no problem here. So if this is the case, then we can thought of our starting material to be this molecule. So here if we charge this with an strong base, what would happen here? It is two acidic protons are there, so base would abstract one of them and make it a negative charge over here, and then simple substitution reaction SN2 would drive us or would make this molecule. So you can see the difference between these two approaches. One approach we make the two bond disconnection, make two appendages, and by 4 plus 2 cycloaddition reaction we can make the molecule, and other way around is we just disconnect one bond and break the ring, so it is known as ring disconnection. So this is RGD, right? So these are two approaches, and this is the difference between ABD and RGD. And and uh, and in the synthesis point of view, we have to say that this approach is more easier than this. So for this case, the APD disconnection is more favorable, but obviously this is also an option you can take. And these things, the APD, RGD, and other FGIs, all are the tools to enable you for a complex, when you approach a complex molecule. So with these tools, you would able to make the bond disconnection properly and make small fragments, and you can find a feasible, economically feasible, also chemistry wise favorable path to synthesize that molecule. So this is the one of the doubts one of you have. So this is it. And one of the next doubts in the previous class was the Barton nitrile ester reaction. So it is mistakes from our side, because it is just typing mistake. It is not nitrile, it is nitrite. So I want to rectify the name. It is Barton nitride ester reaction. So if the ester reaction is there, you all know the nitride esters are this kind of moieties, and nitrates are this kind of moieties. So it is not nitrile, it is nitrite. Now I hope is uh, this is clear now. So this is just a typo thing I have addressed. Now let's start to today's the problem. So this is our first problem. So uh, so this is the question. With this molecule, they have charged with in butyl lithium, and then this DMF they have added. So let's see what would happen first. So with this molecule, at first, this type of lithium species, they coordinate like this, and the ortho hydrogens are there. So this lithium can easily approach uh, this kind of protons and make it, you can do the exchange and make this type of lithiated species, right? So this is and this is an ortho-directing group. So not only OMe, there are many groups that can do the same thing. So I would go discuss in detail in next slide. So for the sake of this problem, let's see the next step. So next step, they have used this with ME, right? So now this is an nucleophile, because the lithium, it is highly electronegative position, and it can attack over here, and this is an electrophile, and then Me2 can leave. So the product would be CHO, the step formyl group incorporation. So the right answer would be B. So yeah, this is also generated, but of course this is not isolable and this is very reactive species. So this is one of the intermediates, but you cannot never isolate this one. So the right answer will be B. And C is incorporation of CO2H or CONME2. So these are the electrophile they have given this. So incorporation of this is not possible. So these are not the right option. So just to check off your knowledge, so how we can incorporate CO2 group, H group there. So in spite of this, if we use CO2, the carbon dioxide, then CO2 H can be incorporated, and for this probably any fluoro, or let's say this kind of molecules, if we use, this can be incorporated. So let's discuss this ortholithiation concept in detail. So this is called an directed orthometallation. So you can see in the previous problem we have here and OMe group. So not only OMe group, there are many other strong directing orthometallation groups. You can see listed over here, and what should be the nature of this group. So these groups should be able to effectively coordinate with alkyl lithium groups, or alkyl lithium species, and in order to establish an this complex induced proximity effect, and the same time be poorly electrophile, so that not react with nucleophile. So of course these are the some criteria for a good directing orthometallation groups. So you can see some of them are listed over here. So you can see that there are some groups like oxygen or nitrogen. They can easily coordinate with lithiums and do this thing. So you can see here the mechanism is written. So with lithiated species, as first this coordination is important. That's why this DMG groups needs to have one oxygen or nitrogen, so that this interaction is very much important for that. And next thing is that removing of this proton. So after removing of this proton, the RH is generated and lithium incorporated over here like this, and obviously this stabilization is there. Then the electrophiles. So what are the electrophiles? I have listed over here. Here it is for formylation. The DMF is used for, let's say you want to incorporate one alcohol moiety over here. So ARCHO you can use. If ARCHO is if you use, so here OH, yeah, this group you can incorporate. So there are many things, many electrophiles like that. So I have listed over here. You can go through it when I use, and I share the slides in the Google Drive, so you can have a look which are the electrophiles are generally used for this kind of ortholithiation reaction. So now I want to discuss about the reaction procedure also. So here you can, for the sake of the question, here it is normally written as n-butyl lithium, but when we practically do the reaction, the reaction medium are generally like THF or ethers, and one important, I must say the very important additive we we give in the reaction mixture is TMEDA. So what is TMEDA? Is tetramethyl ethyl diamine. So this moiety, this amine, this compound. So this let me erase that. So this amine is very much important for this kind of reaction. So why? Let's see. So in like lithium species like n-butyl lithium or secondary butyl lithium or tertiary butyl lithium, all these lithium species are in the reaction mixture at first remain in this type of aggregate type of form, and if it remain in the aggregate this kind of form, the this type of proton abstraction is very much difficult, as lithium are fully coordinated and things like that. So that's why to break this aggregate, we use this amine, this amine, this diamine molecule. So when amine is added in the reaction mixture, this aggregates breaks, you can see, and this kind of species is formed. So, and here you can see lithium is very much free, not in this compared to this aggregation form, and in this form it is very reactive and can do the ortholithiation chemistry. So from here, you can see the same, the lithium coordination is there and the other aggregates is present, and then this the proton abstraction is can easily happen and make this important nucleophile which we need. And another thing in this is the electrophile. I have listed over there, but the electrophile needs to reactive enough, and the reaction mixture have to be moisture free, because if minimum amount of uh, let's say moisture is there, so this lithium can abstract proton from this type water molecule, the moisture. So if that happens, the normal then you would end up with unreacted uh, this molecule, and eventually this type of lithium species would end up you giving the starting material back, nothing else. So that's why the reaction medium we need to keep it moisture free for a good yield and faster reaction. We need to maintain this kind of uh, environment for the reaction condition. So now moving on to the next problem. So this is an easier one. I have discussed earlier also. So let's see. So this is the starting material, and this is in they have used in two equivalents, and the reagents are KCN in ethanol medium. So at first in KCN, what would happen? In, you can see the aldehyde group is there, which is delta plus, or the most electropositive center in the molecule. So KCN, the CN minus would attack over there. So for the sake of simplicity, I am writing this as R. So R, CHO, and CN is attacking. So RO minus CN, and here H. Right. So next, what can be happening? This we have discussed this in the previous class, but again we can discuss this. So ROH and negative charge is generating. So again I want to mention why this is possible, because the presence of this Cn minus group, as this is stable, resonating form is there. So that's why this particular proton abstraction is possible. And next from here, the second equivalent of aldehyde group is present. So it would attack in the aldehyde center. So now things should be ROH Cl. The, the CC bonding is done. So O minus and R. So now nothing. The proton abstraction followed by cyanide removal would lead us to this keto functionality and OH functionality and R functionality. So this should be our product, and we obviously aware of the reaction. The name of the reaction would be benzoin condensation reaction. So very easy question, you can solve easily. So let's see what are the other name reactions that I have listed here. So let me clean these things. Yeah, yeah. So let's say what is a siloene condensation reaction. So in a siloene condensation reaction, the substrates are this kind of ester molecules, and if we add metals like sodium or potassium over here, what it do to an simple one electron transfer, right? So the one electron transfer, uh, the one would occur in the most electropositive center, the carbonyl group, and make it as O minus and dot, right? So you can see this type of uh, species generated, and one homocoupling can happen and make this CC bond. So this radical can do the combination reaction and make this CC bond, and it can generate this molecule. Now what is left? So you can see, and OH, sorry, O minus and OR groups, right? So this negative can push, this can break, this can push, and this breaks. So if this happens, uh, the species should be this. And here, as we are using excess amount of this kind of metals, so sodium is still present in that reaction media, and still can do this electron transfer reaction same way like this. So I am showing over here. So R CO COR, right? So one uh, this type of uh, single electron transfer, again another sodium can do the same thing, so it can generate the O minus and O, and this, okay, for more clarification I'm writing the full. So O minus dot dot minus R, right? Now this recombination or uh, can easily be happening and make this double bond, and O minus is O minus and Na plus is present in the reaction mixture, so the species would be like this. And in presence of water, what would happen? So both can be protonated and make OH and OH, right? Now nothing, the protomerization, this this would lead to this type of alpha hydroxy molecules. So this type of reaction, it starts to this type of uh, alpha hydroxy keto is known as siloid condensation reaction. So in future, if this kind of question came, you can easily solve this. So the next thing is aldol. I am not going to discuss because it is well known, and for asymmetric version, if further questions are there, we definitely going to address those. And next thing is Claisen-Schmidt reaction. So this is probably one of the oldest reaction you have read from the school levels also. So it is nothing like this kind of, let's say this is the starting material, this this type of keto molecules, where alpha hydrogens are present, and in presence of base, enolate can be generated like this. And in this enolate can attack to the one of the second equivalent of the aldehyde molecule, right? Because if we compare aldehyde and keto, aldehyde is more reactive and susceptible for a nucleophilic attack. So this type of enolate can attack this alcohol molecule, sorry, aldehyde molecule, and make this CC bond. Now, in presence of water, the OH is there, and simple and simple elimination reaction of the OH can lead to this type of the condensation product from an this type of keto plus aldehyde to the condensation product, right? So this simple reaction is known as Claisen-Mead reaction of Claisen-Mead condensation. So now, so we have known the other reactions also. So, and for this question we have solved earlier. So right answer would be a benzoate condensation reaction. Now moving on to the next problem. So uh, let's see what. So this is the molecule. They have applied heat, and what would be the product? And here it is 13th level. So let's see. So we can easily do this 1 1 3 2 3. So I am writing like this. So this would nothing but 3 3 sigma topic rearrangement, and simply known as the Claisen rearrangement, right? So let's see what would happen. So at first this bond would break like this, like this, and this. So if this happens, what would be the product? See, so here UT, so here one keto would be there. So yeah, so this type of YT here like this. So here one carbon, here double bond, and then it is 13th element. So here you can see the double bond is forming. So this should be 13th element, right? So this should be the product, and here you can see alpha hydrogen is there, then nothing, the ketoenol tautomerization for gaining of aromaticity, which would lead to one phenol moiety over here, and here the alkyne group, and here it. So let's see, it is matching with not this here, this is wrong, here it is there. So some of one of you have raised your hand. You have any question, you can ask. So two position is like this phenol. So it is our right answer, and also the right answer should be B. It is given like this, and here you can see the OH and the alkyne partner. The relation is 1 3. So both are incorrect. So this is the so the B should be the right answer. So for this case, as it is an asymmetric one, sorry, it is an symmetric one, a planar molecule. So that's why I have easily can do this in this form. But what would have happened if the starting material is stereochemically rich or asymmetric molecule, let's say. So for that case, you always need to draw this type of chair-like transition states. and with this you can easily predict the fate of the reaction in particular stereochemically way. So let's say if for this particular substrate like this, we can write this in this type of chart form, right? So how they have how it is written, so RO, it is they have written over here, right? RO, and then C of this R. So with O, the R is present. You can simply it is like this, and then both the double bonds you can see with it is an E relationship. Also, this is also. So when we are drawing in this form, we need to maintain the same thing. So you can see this is maintained. This is a double bond. These are two in the different direction. So this is E, and this is one, and another one respect to this. So with O is over here. So our triple dash would be in E relationship, right? So or the entity relationship, which is also maintained. If it is maintained like this, and we do the disconnection of this CO, you can see, and make the other bonds, it simply you can uh, predict the fate of the reaction, and it should be in this form. So these are triple dash and R dash. This R triple dash and R dash would be anti to each other in the after the reaction. Let's say if it is not E, it is Z for this case, right? So here you should also maintain in this case the Z. Let's see they have maintained or not. So these two, right? So uh, so you can see this R prime, it is should be in Z relationship with this bond. So that's why here it is in equatorial, and to maintain this Z stereochemistry, it is in axial form, right? So if we do if we maintain this particular thing after the reaction, the R prime and R triple dash would be in same. So this would be a syn product. So as I am discussing the normal Claisen rearrangement, so that's why I thought to incorporate for one of the asymmetric version. If the molecule would be asymmetric, how you can predict the outcome of the reaction in an right stereochemical way. So that's why I have incorporated this little problem over here. So this would help to solve this kind of problems. So this is again in the previous class I have discussed this related to this kind of problems. So the question is, which of the following compound with treatment of HiO4 will lead to these 2,4 pentadiene the pentadiene molecules, right? So with HiO4 we all know the mechanism, but I am discussing again. So this is two orthodiol molecules, right? So what is the general mechanism for this HiO4? At first HiO4 and this type of two diols interact like this, and O is removed, actually you all know I think, and make this type of CO and this OI bond, right? OI bond, and this type of 5-membered kind of species is formed, and then this CC bond would clip, and like this way, which would generate this type of keto functionality and the HiO4 would be left as this byproduct. So let's see for all the cases what should be the product. So we see that in the diol the middle bond is clipped and keto would be formed. So for this case, this this so diols, the middle bond would be clipped, and so what would be the product for these cases? So keto, keto. Again here the same as it is unsymmetric. So if this is for A, these two species are basically both are same. This should be generated. Let's say for B, what would be the product? So this clip, this bond clips. So this is one of the moiety, and second moiety would be so this. Here no keto aldehyde dialdehyde molecule is generated, and for this case, so you can see one to dial. So this right. So this and here HCH, right. So here so two equivalent of formaldehyde and one equivalent of this will form, and here one equivalent of this, one equivalent of this. So here no diols are present, so mostly what can happen is this aldehyde can be converted to CO2H. This is most probable thing, or it may be unreactive. So for the sake of the question, what would generate 2 mole of 2,4 pentadiol. So 1, 2, 3, 4, 5, right? 2 position, 4 position diol. So this is the right product, and also for A we are generating 2 equivalents of this. So that's why A is the right. And for B, we are generating one equivalent of this 1,5 this 2,4 pentadiol, and one equivalent of this dialdehyde. So this is not wrong, and this is also two equivalent of formaldehydes are generated, and one equivalent of pentadiol is generated. So this is also not the right answer. So A would be the right answer. So in this way, you can simply solve this kind of problems. So let's see. This is the next problem. So with this, you all this is nothing but an Wittig reaction, which is pretty well known and popular also. So it is 3p plus CH2. I'm writing like this. So we didn't know why CO2 ET, and we are minus the counter. So in presence of tertiary potassium tertiary butoxide, pretty strong base, tertiary butoxide, and this is an acidic proton, so it can obstruct proton over here. So pH3p plus CH minus and CO2 ET. So as this is an electron withdrawing group, this is an stabilized halide, right? Stabilized halide. So now our Wittig species is generated, and here the keto moiety is over there, so the reaction would occur. So this minus would attack this center, the keto center. So CH is attacking, so O minus there, BPH3 plus like this, and there the one hydrogen is there and one CO2 is there, right? So here to there. Now this O and this electron core. So this would occur from the 4-member ring. So these three, this CO2. Now this ring cleavage generate this one. So this is an Wittig reaction, right? So it is easy reaction, question easily solved. So let's see the other reaction. So Michael reaction we very much know now because it is discussed many times. So Michael reaction is known. So what is Perkin reaction? So probably I incorporated over here. Yeah. So this is Perkin reaction. Let's discuss what is Perkin reaction. So in Perkin reaction, one aldehyde molecule is there and one this type of anhydride molecule is present. In presence of base, it generates two important molecules, one alpha beta unsaturated acid and another equivalent of acid. So let's see the mechanism how things operate. So base here for simplicity it is considered as base. So and then the anhydride here taken is simply this molecule, right? And the aldehyde what they have taken simply ARCH. Okay. Now let's move forward. So what at first the base can abstract proton over here as both and these are acidic protons and both are also symmetric. So no problem, any side you can abstract proton and make the enolate. Now you can see the enolate is generated and the aldehyde molecule in the electrophilic center, the enolate is approaching and making this CC bond. After making the CC bond, it is CH. So here you can see the attack over here. So this CC bond, this particular CC bond is formed. So it is now O minus and arrived, right? So now this O minus can attack this keto center. So if it attack over here, this O minus and methyl can be formed. Now this O minus and breaking of this and stabilization by this. So this type of system is generated and this one CO bond is clipped, you can see. So that's why this particular this species is generated by clipping this particular CO bond. Now another equivalent of anhydride is there and it is a good leaving group which can act also as base. Uh, so that's why OSE minus it can be generated like this also. So this O minus is attacking over here and making and make this or incorporating this over here, and as you can see base is used. So minus is abstracting this particular this acidic proton. You can see only acidic proton left, alpha hydrogen, and it is removing one acid molecule. So one acid molecule is removed. So what is this? This alpha beta unsaturated and anhydride type thing. And now this is also in presence of base, it also can be removed like this. OSC can attack and generate this O minus, which is nothing but acid. So in this way, alpha beta unsaturated acid is generated, one equivalent, and another what is one acid is also generated over here. So where is it? So C3CO2 is another thing, and nothing but this is generated unequivalent. So here, yeah. So here it is. You can see here. Here it is AC minus presence of H plus. So this is the second equivalent, another equivalent. So these two species are generated. And another thing is Claisen reaction. So I think all know, but let's discuss. So what is Claisen rearrangement? You all know. So what is Claisen condensation? So Claisen condensation are nothing but here nothing but the CC bond formation in ester. So let's say this is our molecule. So I am discussing in context of Claisen condensation reaction. CH3, let's say this. So it's an ester molecule, and if we uh, treat it with some base like OMe minus or any strong base, it's sodium methoxide, so it would generate or it would abstract proton from here. It is as it is an alpha hydrogen and K acidic. So CH2 minus OM, and this is, you can see, this is an enolate, nothing but an enolate. CH2 minus OM, right? So this is how the one enolate is generated. Now in the reaction mixture we are seeing the ester molecules are present, and this is an electrophilic center. So this is a very feasible attack, and this would generate the CC bond. So O minus, the CC bond is formed. So CH2 CO, sorry, CO OMe, and here another OMe is there, right? Yeah. So now this type of characteristic removal of an OMe group, CH3 CO CH2 CO OMe, right? So if this type of reaction happens, so this would be known as Claisen condensation reaction. So these are the other things I have discussed. Other options, what are the reactions, and this is I have already discussed. So right answer would be Wittig reaction. So in context of Wittig reaction, I am going to give some more clarification about Wittig reaction. So can someone raise hand? So if you have question, please ask. Seems like not. So yeah. So we all know. So in this is the context, in the context of Wittig reaction I am discussing. So in our problem, we can see we have an stabilized Wittig elide. So actually there are two kind of elides can be in the are possible actually. One is the stabilized and another thing would be unstabilized. So why it is unstabilized Wittig? Because this carbon ion species, the negative charge can easily be in conjugation with this type of keto, ester, cyanide or electron withdrawing groups, and with this resonance stability, this type of resonance stability, for this type of resonance stability, this is known as stabilized elide. And for the unstabilized elide, you can see there are no stabilized or electronic equally withdrawing group are present. Normal alkyl groups are there which are not which cannot uh, stabilize this type of carbon ion, so they are known as unstabilized elides. So, and these two type of elides are pretty important for the reaction also. For the general rule, it is known that the stabilized elide to Wittig reaction, and it gives E selective olefins. What is E selective olefins? Like this. So if we use an stabilized elide, it would give us E stereo E geometry, and for unstable elides, it always gives Z geometry, right? This one pretty well known rule. You can remember to be very beneficial for the solving of our coming problems. So let's see why this kind of how this kind of selectivity appears. So when we are using an unstable light, not stabilized one, so the it is said to be approaching like this kind of this type of perpendicular approach to molecules approach. So you can see this is an unstable light, and this is what one of the substrate which is aldehyde, right? For this for here it is considered aldehyde. So it appears in such fashion for that uh, the steady propulsion of these two species should be minimum. So that's the driving force for this type of approach. So here you can see the groups, the large groups, the R group and P are in are kept in the maximum distance, and this is the to minimize the interaction between these two are the driving force for this type of uh, approach. So if this approach is like this, you can see, so this bond is forming and this bond is forming and becoming planar. So from this type of viscous arrangement to planar. So when this planar type of thing is coming, so then this R and H are coming in the same plane. So when we will do the disconnection, it would lead us this type of Z geometry, C geometry, right? So this is for the case of unstable lines particularly, and you can this, and obviously in the product the repulsion is there, so product is not stable, but this approach is feasible. So for this case you can say it is an kinetically driven product, because kinetics, the approach drive the product formation, not the product stability. So this is an kinetically controlled or kinetic product, you can say. And for the stabilized light case, what happened if the uh, for sim you can consider same kind of approach to try to keep the two bulky groups apart, and can form this type of four member ring. Like this is similar, like same it can form, but here is the catch. For the unstable light, you can see this is irreversible error, so it cannot revert back there, right? Because the light is very much unstable, so the system would not or would not generate the unstable light again. So that's why if when it formed, it cannot be drive back. So this is an irreversible process, this particular step. And from here it has so from here the molecule has two choice: one to form this type of molecule or generate an unstable. So molecule generally chose this, and that's why we have the Z product. But in the stabilized light case, this step is reversible, because this is unstabilized light, and molecule can easily generate and two stable molecules. So if it is unstable or and to stable species and can be regenerated, and then the the TCP or the thermodynamic control wins, because if this happens, so kinetically this is favored, but thermodynamically what is favored? Of course this, because this R and this CO2Me group are in opposite fashion, and for that it is more stable. So that's why when in kinetically control initial stage of the reaction this form, but as it is a reversible reaction, so it would again regenerate this two species, and then thermodynamically controlled way this this stable species is generated. And now from here, if the when we do the disconnection, we would uh, generate this E alkene, uh, E alkene in measured amount with compared to this Z alkene. So this is how the selectivity came from the halides. The stability of one stabilized halide drives makes this particular four-member ring formation reaction reversible. That's why the TCP control came, and Z E alkene is generated. And for this case, as it is an irreversible process, so revert back is not possible. That's why the only Z alkene is formed. So this is an pretty selective reaction also. If we use uh, stabilized light, we would give E alkene in major amount. The ratio would be 20:1 or even higher. So this is a pretty selective reaction and well known also, and it is used in natural product synthesis on total synthesis. Well established thing. So that's why I decided to incorporate this and explain this particular concept. So in this way, we stabilized and unstabilized, we can control the stereochemistry of alkene, and we can synthesize our required alkene easily. So in context of this olefination or this keto to alkene or aldehyde to alkene, so there is another one of the another nice reaction which is Julia olefination. For this case, you can selectively synthesize and E stereochemy is E geometric product or E olefin. So this is also an well-known reaction. So there are other olefination reactions. Most popular are Julia olefination, and another one is of course the Wittig reaction, and one and several others are there. So in coming classes we will cover that also. So let's see which and one of the important one is that Julia definition. So let's discuss this. And another one is Peterson definition also there. So let's see what is Julia definition. So in Wittig reaction, we are using halides based on phosphorus molecule, right? PPH3 or PR3. But here in this Julia olefination reaction, the halides are sulfone based. You can see the SO2, the sulfone based molecules. So with butyl lithium, at first the proton, the alpha hydrogen is abstracted, and this type of species is generated, and then this attack is over, and here it is discussed well. So let's see what is the fate actually. So with butyl lithium aldehyde and one R3X molecule, this type of species at first form, and then in presence of some metal, you can see here the sodium Ag amalgam is used in presence of ethanol. The major amount, this type of three molecule is generated. So let's see the mechanism. What is the mechanism? So at first, with presence of butyl lithium, one alpha hydrogen is abstracted. As you can see, both hydrogens are very acidic, as it is stabilized by this SO2 in the sulfur group. So here in this like this, the anion is generated. Now what would happen? This can easily attack over here and make this O minus. So this species 3 is generated. Now R3X, right? So generally this is used because we need to eliminate this. So uh, uh, to make this O minus as good living group, we do this type of thing. So generally ORR OS is like this good living groups, right? So after this generation of this molecule 4, the sodium amalgam is charged in the reaction mixture, and sulfone and this OR3 removed, and this alkene moiety is formed in, and the relationship is E, right? So let's see how this E geometry is forming. So when we are using the sodium H amalgam, the one electron transfer reaction is at first occurs, right? So here you can see that S dot and OM, the, means the homolytic cleavage of this one one electron is transferred here. So S dot and O in and metal position is nothing but O in A, actually O in A, right? And here S dot. Now this is a good living group, and this sulfur would prefer to not to be in this S dot form, so that's why it removes as PH SO2 in. So in this form, the this particular group is removed. Now what is left? So here one radical is generated due to cleavage of this particular carbon sulfur bond, right? So here you can see the one radical is generated, and here the other group. So here you have already said actually is that OR3 is nothing but good living groups like Oasis. So here it is written as Oasis. Oasis. Now the these metals are present, so one more electron can be given over here, and it can be negative, right? And then this negative can easily remove this OAC group and make this double bond. Now you can see when the negative particular this species, there are two type forms can be possible. One is like this, mm, where where this uh, so as it is an E2 type of elimination, this electron cloud and the living group OAC should be in this type of antiform, right? So E2 kind of, or one kind of elimination here it is happening. So E1 type of, but this type of anti-rearrangement is required for the final elimination. So in the let's see here, this in this particular anti-rearrangement, you can see this H and this H are opposite to each other, or mainly these are an unprime, because this is an arrangement is more stable as due to low steric crowding. But for this case, these are and these are in the same position, so lot of steric index are there. So that's why the molecule should prefer to be in this particular form. So that's why after elimination of OAC, this would lead to the particular E geometry, not C geometry. So that's how the particularly E geometry is formed in the Wheeler olefination reaction. And in Peterson olefination also some control are there with base or acid. In coming classes, I would discuss about that also. So, this is in context of this olefination reaction. For the 5 I have discussed, and the right answer you have already I have discussed one. This is waiting. So now moving for the next problem. Yeah. So this is the next problem. So let's see what is written. So which of the following alcohol could not be prepared by hydride reduction of the corresponding carbonyl compound. So let's see how we can progress. So could not be prepared by hydride reduction, right? So hydride reduction, what are the hydride reductions? H minus nothing but how we do the hydride reaction. So for that reagents are NaBH4, LiLH4, like this kind of reagents, right? And with this type of aldehyde molecule or keto molecule, when we use this type of reagents, it nothing but the hydride transfer happens and make the secondary alcohol or primary alcohol. So this is the hydride reduction. So if we are saying which of them cannot be prepared in this way, so let's see. So this is for one. So how it can be prepared? So on the corresponding alcohol, if we do the NaBH4 treatment or NaBH4 or LiLH4, this would lead to this. So this can easily be prepared by hydride reduction. So one is not the right option. So let's say for the two. So this is the second molecule. This can also be prepared by reduction of this keto moiety, right? Because H minus can attack over here and generate this alcohol. So this is also possible by hydride reduction. So now let's say 3. Yeah. So you can already see this is not possible. So here ETOH. Right. So now if we want to do the retro, there no hydride is there. There it is ethyl. So if we want to prepare this, we need second ring, right? Second ring, okay. Keto, and another thing would be required this kind of species, right? Because we need to incorporate one ethyl group over here, not hydride. So here with hydride, it would be the only secondary alcohol. So with hydride reduction, this is not possible. And why? And what is they have asked for? Could not be prepared. So 3 could not be prepared by hydride reduction. And let's see 4. Right. So for 4, OH, and here you can see it is and primary alcohol. So primary alcohols can easily be made from this if hydride transfer is there. So this is possible. So that's so hydride reduction can with hydride reduction we can synthesize 4. So this is also not the right answer. So right answer should be 3. So from here it is the detailed view for the for, for the for this kind of this type of problem, but simply you can also think simply. So let me clean again. Yeah. So simply you can think like, so with hydride reduction we only can do these these two cases, right? So with hydride transfer, there are one primary alcohol or secondary alcohol. So primary alcohol or secondary alcohol. These two can be prepared by hydride reduction. So what we need to see here only where we have an tertiary alcohol and only tertiary alcohol. If tertiary alcohol is there, hydride reduction cannot be formed. So let's see in this simpler approach. So this is primary can be formed, secondary can be formed, tertiary it cannot be formed. So this is our answer, and this is also secondary and tertiary. So secondary is there, a primary is there. So this can also be formed. So in a simpler way also can approach this problem. So let's see for the next one. This is simple aldol condensation reaction. So let's see. So in our reaction medium we have this molecule. We have this molecule and this molecule, and we are using NaOH with heat. So with heat it is very important for the for the sake of the reaction or the solving approach. So with heat we always generate an KCP or kinetic or TCP. So thermodynamically stable enolate we will dominate in this particular reaction condition. So let's see how many uh, enolates are possible. So one of the enolates is this. Second enolate should be this one, and another, and from here also many possibilities are there. So one of the thing is this, and next thing would be this. So among them, uh, we draw the enolate over here. Minus double bond. So there are 3 alpha H's, 2 alpha H's, 6 alpha H, oh, and more. And again, so 8 alpha hydrogens are there. 3, 4, 5, 6, 7. Sorry, 7 alpha hydrogens are there. So it which is so it is most substituted enolate and stabilized by this hyperconjugating effect of the alpha hydrogen. So that's why this particular enolate is TCP. And here you can see only if this happens only two are there. So only two are there, two or three are there. So this is not this is so this is only kinetically stable. So in presence of heat, only this thermodynamically stable product will will be the major one, and so this particular enolate will be generated as this is an TCP condition. So oh my, so this is a stable enolate. Now the next species would be this. So here you can see again two possibilities, but when enolate is attacking, the soft combination is preferred, right? So this attack is preferred like this. So Michael addition or 1,4 addition. So if this addition is like this, let's see what is the intermediate we have generated. So here 1 methyl, the keto group, and here this. Here the negative charge is generated, and in which is used means it is an aqueous in which, so H2O is there, so it can easily be protonated like this. Now after formation of these, again we have OH minus, right? So again the enolate formation is possible. So if enolate formation is happen over here, let's see, here the alpha hydrogens are there. So OH minus would abstract proton from here and make this enolate. So minus this here, so particular this atom. So here we have generated 6 5. All are 6 5 fused step. Here one methyl. Here attack is here, right? So here OH or O minus or in OH, let's say. Now the condensation can be happening, so you can think of an E1CB type. At first electron withdrawing, at first one proton withdrawn and this negative is formed, then this formation of the double bond over here. So this would be the final product, normal aldol condensation type. Next step, so the product would be this. So now let's see with which it is matching. So here it is intermediate, so it would not so this is the previous, so it is not stop in this step, the negative and elimination would occur, so it is not right. So B, it is completely matching with our mechanistic the mechanism what we have done, so B should be the right answer. D is also the one of the previous intermediate, this bond formation would happen. And oh, here one thing is wrong, no methyl is there and here no cycle, so the right answer would be B. So B is the right answer. So and from here we are generating actually this, the most stable one, but as we are applying it, but let's say you are at first removing the proton from here, then what would be the case? This, so this would be an 4 member, right? So this is not, that's why this is not occurring the 4 member, so that's why this enolate is attacking here and the reaction is going. Another possibility would be here to here. So if that happens, let's see, probably if that happens, it is like one of the strain system. So you can see one, one, two, three. So you can see already see the strain, one of the strain system or the BZ type of system is generating if this attacks over here. So that's why this is also not happening. So only this is attacking over here and making this 6 5 fuse system. So in this way you should approach and predict the product. Now let's see the next one. So it needs to write. So it needs to. hydrogen Na plus NH2 minus. So this is an acidic proton. So that's why strong base we are using also. So with this piece is the negative, so negative, and Na plus is stabilizing. So this type of species is generated at first, right? So you already know, I think, but as the hybridization is sp, that's why the acidity is more and this abstraction is possible now. And the electrophile given is in butyl iodide. So 1 2 3 4 iodide. So this is electrophilic center, and this is our nucleophile normal SN2 attack, and which would lead to this particular molecule 1 2. Remembering is the alkyne is missing. Yeah, so the alkyne part, then 1 2 3. So this species is generated. Now they have said what H2 Lindar's catalysis. So Lindar's catalysis, you all know probably, this is palladium with CO3 and some catalytic poison like PB are there, and I will be discussing what is Lindar's catalysis. But for now, problem solving. So Lindar's catalysis and H2 do the syn hydrogenation reaction, means if the triple bond is there, from here only Z geometry alkenes are formed. No further reduction is happening due to some poison like PB are used. That's why. And the bottom line should be that from alkyne to Z alkene. That's the role of this hydrogen and Lindar's catalysis. So with this H2 and Lindlar catalysts, so these four, and with the catalyst here 1 2 3 4, and here hydrogen. So this should be the product. So let's see the here the Z geometry in butyl, which is this in butyl group, and this group. So is the answer. So here it is E geometry, which is not right, and here in profile, means they need to say further fully, if the full reduction is there, then only not profile mean butyl. So this is also not correct also, as this is the product. Profile would be only 3, but here other things are there, butyl and molecules. It is also not correct. So now let's see how this H2 Lindar's catalyst do the syn reduction. So here it's the general reaction scheme for this Lindlar catalyst. So here this palladium and calcium carbonate in presence of this this PB lead, it is act as poison. So that's it actually, and the quinolin also. So in these two actually reduces some catalytic power of this palladium. That's why it stops in this form, alkene form, not further do the reduction and make a simple alkane chain. So to stop this process, these two, palladium and quinoline, lead and Pb is used. So now for the reaction mechanism, you can see with palladium acetate and quinoline, this kind of species at first generated, then normal, the alkyne, the tricloud and the palladium, they interact and make this species. Now when this particular species is formed, you can see, so this is alkene, and from, let's say, bahite or above, and you can consider the this whole palladium thing is there, right? So in this way, from, let's say, you consider from behind, the palladium is uh, having the interaction with alkyne, right? So in this way, the back side of this alkyne is blocked, so hydrogen cannot incorporate or react from the back side. Only one side is free. So that's why two hydrogens should be the same in the syn side. So as to make the anti one proton come from here and another one should be back, to if we want to make the E thing, but here we are making only Z. So that's why, for that reason, actually the palladium blocks the whole background or backside or above side, so that face is completely inaccessible by the hydrogen. So hydrogen have to uh, appear or interact from the same face. So that's why the scene or the jet geometry is generated by this type, by this particular reaction condition. So that's the reaction mechanism for the insular catalyst. Now let's see the next problem. Here cyanide and here one nucleophile is there. So cyclohexane ring cyanide group, and here this is our nucleophile. So this is electronegative and here it is electropositive. So this attack is possible. So N and here this. So N minus and proton is H plus is there, so it is NH, right? But H plus means actually H plus aqueous H plus. So in this particular reaction condition, it is susceptible for hydrolysis. So how hydrolysis happens? It is simple. I am writing it in general form. In H, it interact with H plus and make it like this, and H2O is there. So this attack is possible. So with this NH2, OH and R, like these things possible, and then simple removal of ammonia. Here also one H plus is removed, OH2OH. So ammonia is removed. So in this way, simple hydrolysis from this type of imine to the keto, the imine hydrolysis, the keto is formed. So let me keep these things. So here too, one keto would be generated. Yeah. So from here, keto group is generated like this. So now what is the second condition? Wolff-Kishner reaction, well-known reaction. The hydrogen hydrate, it is in this form, and strong bases like KOH or NOH, generally KOH are preferred. These are the reaction conditions. Now let's see with if we treat this with this particular NH2, NH2 and KOH. So it is have an alpha effect also, very good nucleophile. This attack is possible. I am writing is R and R prime, right? So R and R prime. So R and here actually the condensation reaction well known. So I am writing this at this hydrogen from. Right, it is well known. So in H2 is attacking, then one electron push and water is removing. So normal condensation type you can consider, which make this hydrogen. So when this type of hydrogen is formed, and one thing is that very high temperature is required over here. So when OH minus is there, so this abstraction can happen. So R prime minus double bond NH, and this abstract one proton as it is an aqueous medium, right? So one proton is abstracted, R prime, and this. Now second, another equivalent of base can abstract proton from here and make this type of moiety. So nitrogen can be removed, and RR is and one minus is there, and in water medium is abstract proton. So the conversion of the Wolff-Kishner is RCO R prime to RCH to R prime. So this is the reduction for the this particular two condition. So with that, let's see. So with Wolff-Kishner, so what would be the word from here? If here to CH2, right? So here CH2. So let's match. So A should be the answer. Here keto was there. Is reduced. This is the right answer. Here CO2H, CHO and alcohol. So these are the wrong ones. So A should be the answer. So so the practically point of view, when an keto or aldehyde is reacted with this sort of hydrogen hydride, this hydrogen is quite stable actually. Sometimes molecules stays in this particular form, so that's why after that we need to use much or very much excess equivalent of base and heat to remove the particular nitrogen and do the reaction. So this thing happens with me. I also faced this. So although it is written, you can see here it seems very easy, but in practically it is a very vigorous reaction. We need to hit the reaction condition probably greater than 150, 160, and QE is also required in 5 to 10 equivalent. So this is some practical aspects, and let's see the next or the last question today, I guess. Yeah. So this is the about one of the substrate, and this BH3THF. Let's see. So with BH2, you all know how the interaction happens, like this and this, right? So the thing is that let's substrate side should be interact with the boron molecule. here BH2, or it refers to being Br3 from right. All know that. So when we use the H2O2 in Br3, R R R H2O2 in OH, so it is in this form. As with from here, this species is generated. So this. So now one uh, one shifting like this happens. This kind of shift. So BRR and OR, this, and from here in the same process BOR3 is generated, and in presence of water ROH is generated. So the bottom line should be that from uh, so you can see, so where the current is attached with the carbon, there the incorporation of one hydroxy group. So here same thing would happen, and carbon reduction and OH is incorporated, right? So this should be the product after B, and now it is charged with PBr3. So PBr3, let's see what happens. So with PBr3, at first this type of species is generated. You can see the PBr3, one Br minus is removed, right? And this attack is possible, and like this way RBr is generated, SN2 attack of Br minus. So simply you can say from this the product should be CH2Br. So this is our product. Let's see. So A wrong position, Br so not correct. B should be the answer. Yeah. And here two bromine are incorporated. This is not the case. So B should be the right answer. So yeah. So this is end of today's problems solving and some uh, yeah. So today I have discussed this some assignment problems, some of the uh, doubts from the previous class I have also discussed, and some new concepts which are required to solve the problems which are discussed. So very thank to all of you who have stayed, and so if and probably some of you are going to watch it later, so uh, to watch and let me know if there are any suggestions, is there any doubts. You can also mail me or put and comment, so I will definitely going to address those questions. So thank you for joining, and we will meet in the next class. Thank you.